Yes, dear students, in the last class we have studied about the stability of metal complexes. In the stability, we have studied the two types. One is thermodynamic stability, another one is kinetic stability. And we have also studied that the thermodynamic stability and kinetic stability, they are not interrelated to each other. A complex may be thermodynamically more stable, but it may be kinetically labile. Similarly, a complex may be the thermodynamically less stable or kinetically inert. Now, this is what in the stability we have discussed in the last class. That's why I have said in a last point, one particular complex may be stable towards a reagent and highly reactive towards another reagent. Today, let us study about the factors affecting the stability of the complexes. The stability of a complex depends upon the nature of the central metal ion and the nature of the ligands. Now let us know about the nature of the central metal ion. So the stability of the complex based on the central metal ion depends on charge on the central metal ion, size of central metal ion, and electronegativity or charge distribution of the metal ion. Let us take some of the examples. It says greater the charge on the central metal ion, greater is the stability of the complex. Let us take an example, that is hexacyanoferrate 3, which is also called ferricyanide ion. Its log beta value is 31. And another complex, hexacyanoferrate 2 or ferrocyanide ion, its log beta value is 8.3. From the log beta values, so we come to know that the greater the log beta value, greater is the stability. Hence, the Fe3 complexes are more stable than Fe2 complexes. As the size of metal ion decreases, the stability of complex also increases. Let us take the manganese, iron, cobalt, nickel, copper and zinc, which are all in +2 state. And when I take the ionic radius in picometers, from manganese to copper, ionic radius decreases, and from copper to zinc, it increases. This is due to the complete filled d orbitals in case of the zinc. The order of stability in these cases is manganese 2 complexes are less stable than Fe+2 complexes, which are less stable than cobalt 2, and further less stable than nickel 2, and further less stable than copper 2, whereas the copper 2 complexes are more stable than the zinc. That is, the zinc complexes are more stable. And now, coming to the order of stability, this type of order of stability is called Ewing-Williams order. It is also known as Ewing-Williams order. Now, from this it says, smaller the size and larger the charge of a metal ion, more stable are the complexes. This is because a smaller, more highly charged ions allows closer and faster approach of the ligands, and the greater force of attraction results into stable complex. Very, very important, the statement to be remembered. Next, another point let us we consider. Metals are classified into class A and class B metals. And also they are given as borderline metals also. Here I have given a classification. So this classification was given by Chart and Herland. And according to a class A metals, it includes hydrogen. Here the metals means we should not take as a basis like metals are solids, but it is based on how they give the electrons. We call the metals also the elements which gives electrons are metals, and the elements which accepts electrons are non-metals. Based on this, the class A metals includes even the metals like hydrogen, because hydrogen gives electron. Alkali and alkaline earth metals, scandium to chromium, aluminium to chlorine. So the chlorine is a non-metal, but in some of the interhalogen compounds, the chlorine accepts the electrons. Sorry, it gives the electrons. Zinc to bromine, indium, tin, antimony, iodine, lanthanides and actinides belongs to class A type of the metals. Coming to the class B type of the metals, which includes rhodium, palladium, silver, iridium, platinum, aurum and mercury. And some of the metals which are a borderline metals, they are neither a class A or they are the class B. In between them, they are manganese to copper, tantalum to polonium, molybdenum, technetium, ruthenium, tungsten, rhenium, osmium and cadmium. Now, class A metal, the same thing I have given here, which includes the class A metals. All these class A metals attract electrons weakly. They form most stable complexes with those ligands having electronegativity of atoms of such ligands contains nitrogen, oxygen and fluorine. So in the class B metals, these metals form most stable complexes with pi acceptor ligands containing the phosphorus, sulfur, arsenic, bromine and iodine. Coming to the second type, that is the nature of the ligands. Stability of the complexes depends also on the size and charge of the ligands, basic strength of the ligand and presence of ring structures in the ligand. It says small size of the ligand with higher negative charge form stable complexes. For example, the fluoride ion forms more stable complexes with Fe3+ than the chloride, bromide or iodide ions. This is due to easy approach of the ligand towards the metal ion. Now, if I take an example, hexafluoroferrate 3 complex, its log beta value is 6. If I take hexachloroferrate 2 complex, its log beta value is 1.3. So this shows that the first complex is more stable than the second complex. Similarly, large perchlorate ion, ClO4- ion is known as a perchlorate ion. Its size is very big, has relatively small tendency to form metal complexes with chloride ion. In a similar manner, A small dinegative anion like oxide ion forms more stable complexes than does the large sulfide ion. So in general, say a metal ligand bond involves the donation of electron pairs from the ligands to the empty orbitals of the central metal ion. Greater the ease of donation of electron pairs by the ligand, greater is the stability of the complexes formed. In other words, strong ligands form most stable complexes than the weak ligands. Hence, complexes containing cyanide ion and ammonia as ligands are more stable than water as ligand. Coming to the third one, presence of ring structures. Some of the multidentate ligands form most stable complexes due to the presence of ring structures in the complex. Such ligands are called chelates. Anyway, you are going to study about these chelates in this class after. Now, here I have shown a slide. In general, the factors affecting the stability of complexes. In the factors affecting the stability of complexes, coming to the first one, the nature of the metal ion. So, the increase in charge on the metal ion increases stability of complex. Similarly, decrease in size of metal ion increases stability of complex, and increase in charge size, it increases stability of complexes. Lastly, more electronegative metal ions form complexes with ligand having donor atom of high electronegativity and vice versa. Here also I have shown about the various factors that affects the stability of complexes. So here also it says the smaller, the same thing what we have discussed. The smaller an ion gives greater is its electric field and more stable the complex is. Metal of higher charge give more stable complexes. This is what I have said. The +3 complexes of iron are more stable than +2 complexes of iron. The higher acidity or electronegativity of metal, the higher the stability of the complex. So, metals which has incomplete outer shell have more tendency to accept electrons, hence they are more stable complexes. This table also shows about the stability what we have discussed so far. That is the nature of the metal ion, nature of the ligand and basicity of the ligand. Now this is also one more the factor affecting the lability of the complexes. The same thing what we have discussed in the just now. So this is about the factors that affects the stability of the complexes. Now coming to the another term known as the chelates. The term chelate was first introduced by Morgan and Drew. Chelates are the complexes in which the donor atoms are attached to each other as well as to the metal to form a heterocyclic ring. Here the meaning of a metal means metal ion. So I repeat, the chelates are the complexes in which the donor atoms are attached to each other as well as to the metal ion or metal to form a heterocyclic ring. Chelate is composed of a metal ion and a chelating agent. So the chelate, it is composed of a metal ion and a chelating agents. The chelating agent is a substance which can form several bonds to a single metal ion. These bonds may be either covalent or coordinate. Chelating agent is a multidentate ligand. So, chelating agents are always multidentate ligands. They donate, it may be a bidentate, tridentate, tetradentate, or even hexadentate. The examples of the chelating agents are ethylene diamine, oxalate, glycine, orthophenanthroline, EDTA. EDTA means ethylene diamine tetraacetic acid. It may be a tetraacetic acid or it may be the disodium salt of EDTA. Covalent bond is formed by the replacement of a proton in an organic group such as carboxylic group, sulfonic group, the oxime group, enolic hydroxyl group. And in such cases, the proton is removed and a covalent bond is formed between the metal ion and a donor atom. Coordinate bond is formed by the donation of lone pair of electrons without the replacement of hydrogen. Example, the amine. In case of amine, nitrogen donates the lone pair of electron, but hydrogen will not come out. That's why the amine is a base. It is not an acidic functional group. Similarly, OH. It is an alcoholic group. H cannot be replaced. So similarly, we have carbonyl group, oxime group, and thioether groups. Let us take what are the characteristics of the chelates. The chelates have low melting point. They are quite stable. These chelates are more stable than the normal coordination compounds. That's why the people, they are interested to prepare the chelates. That's why they say they are quite stable. They dissolve easily in organic solvents. The donor groups are linked firmly to the metal ion present in the ring. The presence of heterocyclic ring is essential for the formation of chelates. So the chelates are those coordination compounds which contains the heterocyclic rings. This heterocyclic ring makes the complex more stable. The metal ion involved in the formation of chelate should have a suitable size. Chelates form 5 or 6 membered rings. In this ring, the metal ion is also the part of the ring. Chelates are more stable than the normal coordination compounds. Now let us know some of the examples of the chelates. Coming to the first one, platinum oxalate complex. In this platinum oxalate complex, so we have here a ring. So this ring platinum is, so it forms a ring. So we have two rings, that is the two oxalate groups, so which forms a ring. So oxalate is attracted to platinum through covalent bonds. In case of copper glycinate, so the glycine is an amino acid which contain amino group and carboxylic acid group. So through the carboxylic acid we have copper and oxygen covalent bond, and through the amino group, copper and amino group between, we have a coordinate bond. So these are the chelates, how they result. And these chelates are more stable than a normal coordination compounds. Here I have shown the one more example known as nickel dimethyl glyoximate. In a nickel dimethyl glyoximate, so this is the structure of the dimethyl glyoximate. It contains, so we come across one chelating ring is here and other two chelating rings. Totally it contains the four chelating rings, and in one of the ring there is a presence of hydrogen bonding. This chelate contains the two covalent and two coordinate bonds along with hydrogen bonding. Coming to the factors influencing the stability of metal chelates. What are the factors? The similar factors what we say about the stability of the complexes, same factors are also responsible in this case, like the size of the chelate ring. Chelates with 5 or 6 membered rings are most stable. So, increase in the number of rings within the chelate results greater stability. Platinum oxalate and copper glycinate complexes contain 2 rings, whereas the nickel dimethyl glyoximate complex contains 4 rings. Hence, nickel DMG complex is more stable than the other 2 complexes. The stability of transition metal chelates decreases with increasing basicity of the metal. The transition metals which form the strongest covalent bonds with the ligand molecules produce stablest chelates. So these are the various factors. Now in the slide I have shown the various chelating agents and also the chelates. So in the first one, so it is ethylene diamine. So this is the ethylene diamine and it forms a complex with platinum, and we have one chelate, that's a 5-membered ring, and other are the 2Cl which donates a lone pair of electron. In the next is the nickel dimethyl glyoxime, which I have shown here the 2 chelating rings, and later on that OH groups also forms a hydrogen bonding resulting the 4 rings. In this also I have shown the various ligands, and here iron is bonded to porphyrins. So it is one of the a chelate that is present in the human blood. So we have the various other the examples with EDTA, the metal ion forms. EDTA acts as an hexadentate ligand. This is also, it forms a chelate. Now here also I have shown the various the chelates and how they have formed the rings. These chelates have very wide applications. So that applications or the importance of the chelates, let us we know. We know the chlorophyll present in the plant and heme present in the human blood are the examples of the chelates. Chlorophyll contains Mg2 plus ion and heme contains Fe2 plus ion as the central metal ion in the chelate. And we know chlorophyll is responsible for photosynthesis, and heme present in hemoglobin of the blood is responsible for transport of oxygen in the human body. In qualitative analysis of nickel, magnesium and aluminium, ions in solution are characterized by the formation of stable and highly colored chelates. Thus, dimethyl glyoxime, 8-hydroxyquinoline, orthophenanthroline, Fehling solution aluminum, etc. are the chelating agents which are used as chelating agents in qualitative analysis. Chelating agents are used even in gravimetric analysis of magnesium, nickel, etc. by their quantitative precipitation. The advantage of the precipitate is they have the low metal content, and this makes possible the determination of very small amount of metal with great accuracy. Here the nickel precipitates as nickel DMG complex, the chelate, which is a scarlet red in color, and based upon weighing the precipitate of this, we can find out the amount of the nickel present in the solution. This is another importance. Next, chelating agents are frequently used as indicators in the titration of certain metal ions. Example, ferroin is a chelate complex. It is a orthophenanthroline complex of iron, where iron is in +2 state. It is deep red in color, which is used as an indicator in the redox titration. Here ferroin is oxidized only after the reducing agent being titrated is completely oxidized. Another importance, the chelates are used in water softening processes by ion exchange resins and also in the removal of boiler scales in industries. Chelating agent like ethylene diamine tetraacetic acid, that is EDTA, are used to speed up the elimination of harmful radioactive metals from the body. Chelates, which form soluble metal chelates with precipitates, are used for solvent extraction. Fruits, fruit juices, and foodstuffs are preserved with the help of chelating compounds. So these are all some of the importance of the chelates. Here also I have given in this slide the importance of the chelations and the uses of chelates in nutritional supplements, in fertilizers also. So in 1960s, the scientists developed the concept of chelating a metal ion prior to feeding the element to the animal. This would create a neutral compound. So these are also used in fertilizers, and they also act as micronutrients. Chelating agents are frequently used as, so this we have already studied, and now the next we take. The chelates have very wide applications in pharmaceuticals. So the calcium salts such as calcium carbonate and calcium phosphate are used as antacids to neutralize excess gastric acids. The calcium antacids often cause constipation and are therefore usually co-administered with magnesium compounds. Calcium, magnesium, and aluminium antacids should not be co-administered with certain drugs. So in this, the example tetracycline, to avoid chelation which renders both drug useless. The calcium gluconate IV is used as an antidote in magnesium poisoning, while dried calcium sulfate is used as plaster of Paris. So like this, we have various applications of the chelates. Here I have shown the chelating agents in analytical chemistry. We have NTA, So we have EDTA, DTPA, DCTA. So students, you go through these, which are the examples of the chelating agents. Now, the useful chelating agents. I have given the list of the useful chelating agents like dimercaprol, dimercaptosuccinic acid, dimercaptopropane sulfonic acid, disodium edetate, calcium disodium edetate, penicillamine, and so the various other examples like diferoxamine, propone. Here, these are all the various other chelates. So, where the metal ions, they combine with the chelating agents and forms a very important the components in the cell. These are all the cellular components. We know vitamin B12, which is a very important the what you can say the component. So where you have cobalt as a metal ion inside. Even in carboxypeptidase, we have it is a cobalt chelate. So like this we have chlorophyll, chloroplast, urease which contains nickel, carbonic oxidase, alcohol dehydrogenase which contains the zinc. These are all the various other examples of the cellular components containing the metal ions, which are also the examples of the chelates. Lastly, coming to the drawback of chelating agents. So these are all the list of the drawbacks. That is redistribution of toxic metals. Here the toxic metal also redistributed during the implication or application of the chelates. So sometimes essential metal loss. These chelates, they remove even the essential metals which are present in the living organisms. So like this we have the drawbacks like no removal of metal from intracellular sites, poor clinical recovery, pre-oxidant effect, increased blood pressure, headache, nausea. These are all some of the effects of the chelating agents. Students, go through these aspects and try to learn about these things by repeated reading.